Mic is on. Today we're going to do our lesson on related rates. This is our first application of derivatives. So basically, to understand what related rates are, I want to give you sort of a little bit of an analogy. Imagine you're driving a car and you're driving from here, which we're in Calgary, to Edmonton. And the speed you travel from Calgary to Edmonton kind of changes on your pathway to Calgary or from Calgary to Edmonton. Now, if I was specifically interested in finding what my speedometer said at this instant in time, or perhaps this instant in time, that's what related rates will do for us. So I could be, for example, I could be interested in what is the rate of change of my car when I hit the red deer sign. I would look at my speedometer, and at that specific moment, perhaps I was traveling 112 kilometers per hour. That would be the instantaneous rate of change at that instant in time. So related rates is all about finding a very specific instant in time and how fast some quantity was changing at that specific point in time. So just some steps to help you out. Sometimes drawing and sketching and labeling a graph is helpful. You want to be careful that when you're drawing the graph that the variables you introduce are variables to show distances that change with respect to time. You don't want to put numbers on your diagram unless they are numbers that stay fixed. You want to list all of the values given in math terms or in math symbols to try to get away from the words and start moving into the math. So for example, if they say something changes or the rate of change, we know that that would represent a derivative. So we could say if my variable x changed with respect to time, this would be dx dt. Or if I had a variable y that changed with respect to time, this would be a dy dt. I could talk about an area changing with respect to time. This would be a dA dt. You also want to kind of use math symbols to describe what it is you're trying to find. So I could be looking for a radius, I could be looking for an x variable or a y variable I introduce. You want to use math symbols to help you do that. The next thing would be you want to write an equation relating the variables. So sometimes this could be a known formula like surface area, volume. You could maybe think of Pythagorean theorem or other trig, your SOHCAHTOA information as well that can help you write an equation that relates the variables. And then at the very end, you want to just make sure you work out the answer and kind of put labels on your answers with the units that that variable would represent. So let's go through some examples. The examples that I'm going to go through here are the very popular types of examples that you will see as you move further into calculus and post-secondary or kind of on our assessments. These are kind of the big popular examples. So I drop a pebble into a calm pond and it caused these ripples that are circular in nature, and they are all concentric circles, meaning that they have the same center. And the rate that these ripples are forming changes with respect to time. So at the specific time when my radius is 4 feet, I want to know how fast that area was changing with respect to time. So it's just like me saying, when I hit the red deer sign, how fast was I traveling? 112. That value could be different when I'm at a different location on the pathway from me going from Calgary to Edmonton. So let's take our variables and try to turn them into math. They talk about the radius of an outer ripple. So I'm just going to draw a circle. This is sort of a snapshot in time for one of the ripples. Here's my radius r, and A would represent the area of the circle. So when they say that the radius of the outer ripple is increasing at a constant rate of 1, that tells me dr, dt, the rate of change in the radius, is increasing. So I'm going to use a positive number to represent that that's increasing. And it's increasing at a rate of 1 foot per second. So this is me taking words and changing them into math symbols. Now when I hit the red deer sign is the same as when the radius is 4. So when r is 4, find and they say, what is the total area of the disturbed water changing? We want to find the rate of change in the area. So I've taken my symbols or my words and changed them to symbols. So we need an equation that relates the area to the radius. So I know that the area of a circle is pi r squared. So there's my formula that relates my variables together. I need to take the derivative of this formula, dA dt, and this will tell me how the area changes with respect to time in terms of a formula. So I take the derivative of pi r squared, which would be 2 pi r dr dt. And now I'm ready to sub in all the values I've been given. So dA dt is equal to 2 pi is a constant, radius is 4, dr dt is 1 foot per second, so this gives me a total of 8 pi. And now I need to attach units. So this is saying that when my radius is exactly 4 in one of these ripples, my area was changing at 8 pi feet squared per second. So it's like, again, when I'm using the analogy of the red deer, when I hit the red deer sign and I look at my speedometer, it would be 112 kilometers per hour. But that doesn't mean that when I'm here, it would be the same thing. This could be that I was traveling 92 kilometers per hour at that moment. Okay, so that was a two-dimensional example. Our classic example number 2 will start to move into three-dimensional examples. They can talk about volume or surface area. If I'm in 2 dimensions, we can talk about area, we could talk about perimeter and those kinds of things. With 3-dimensional, we can talk about volume or surface area, depending on what the question's asking. So air is being pumped into a spherical balloon. We know we're dealing with a sphere at a rate of 5,000 cubic centimeters per minute. So if you're not sure what value this quantity represents, you can look at the units. It's cubic centimeters per minute, and when you think 3-dimensional and you're dealing with cubic centimeters, we know we're referring to volume. But because it's a volume per time, we know we're dealing with a derivative. So dV dt is 5,000 cubic centimeters per minute, so centimeters cubed per minute. We want to find, they're asking how fast is the radius, so find dr dt. Find how fast the radius of the balloon is changing. At the instant the radius is 30 centimeters. So when radius is 30 centimeters. So analogously, this is like when I hit the red deer sign. So I need an equation that relates the volume to the radius in a sphere. My volume is 4/3 pi r cubed. And now I'm ready to take the derivative. So dV dt, the rate of change in the volume with respect to time, is you're going to bring down the 3. So the 3's will cancel, 4 pi r squared. And then the derivative of r is dr dt. So you're going to be using a lot of chain rule and implicit differentiation because our variables are changing with respect to time in addition to with respect to each other. Okay, so now we're ready to sub in our variables. Dr dt is what I'm looking for. I'm going to isolate for dr dt by dividing my dV dt. Divide by 4 pi r squared. And I sub in my values now. So 5,000 divided by 4 pi. My radius is 30, so 30 squared. And I'm happy with you leaving your answer like that. Just put some units on it. So this would be centimeters, because that's the radius units per minute. And that would be my final answer. They can ask you modified questions related to this. So sort of the same volume scenario happening, but now they say at the time when the volume and radius of the sphere are increasing at the same numerical value, so dV dt equals dr dt. So when this is true, they want you to find r. So this is kind of the scenario when I hit the red deer sign. So that is a very specific scenario. We already have our relationship between our rate of change in the volume in relationship to the rate of change in the radius. Now, when dV and dV dt and dr dt are the same, and I divide both sides by dr dt, or vice versa, this quantity is going to cancel, but dv dt divided by dr dt is actually just a 1. So I'm going to sub in a 1 is equal to 4 pi r squared. And then I want to solve for the radius, so I'm going to divide both sides by 4 pi. So therefore, sorry, that's my radius squared. I take the square root of both sides. We want to remember that r is strictly positive because we're referring to the radius. So we get 1 over 2, which is the square root of 1 over 4, and then the root of pi that sits on the denominator. And my radius would be in centimeters. So that's classic example 2. They could refer to volume of a sphere, surface area of a sphere, or any three-dimensional object. So they can talk about a cylinder, they could talk about a cone, and we're going to see some of these other problems later. Example number 3 is referring to Pythagorean theorem. So just kind of very cut out Pythagorean theorem problems. And the ladder problem is kind of the most popular. So we have a ladder leaning against a wall, and the ladder is 20 feet long. Now I'm going to use the 20 in my diagram because the ladder's length doesn't change with respect to time. It will always be 20 feet long no matter when I'm dealing with a scenario. Now the base of the ladder, so here's the base of the ladder, is being pulled away from the wall, so it's moving outwards this way, which is causing the ladder to slide down the wall this way. And the base of the ladder is being pulled away from the wall at 4 feet per second. So if this variable represents how far the distance is from the wall to the ladder, the rate of change of the base of the ladder with respect to time would be 4 feet per second. And I would use a positive value to represent that because this x is getting larger with respect to time. So I'd use a positive 4 to represent that. So how fast is the top of the ladder moving down? So I want to find dy dt when the top of the ladder is 12 feet above the ground. So I'm going to use y here. So when y is 12. So now I've translated the words into math symbols. And now I'm ready to write a relationship for how x, y, and the 20 relate to each other. And that's through Pythagorean theorem. X squared plus y squared equals 20 squared. I go ahead and take the derivative. So derivative of x squared is 2x dx dt plus 2y dy dt, because everything is changing with respect to time. And then the derivative of 20 squared is just a constant, so it goes to 0. Now I'm going to continue down here. We want to isolate for dy dt. So I want to rearrange my formula, so I'm going to move that to the left hand side, so that's going to be minus 2x dx dt divided by 2y. You'll notice that the 2's cancel out, so cancel the 2's out, and so my final answer would be negative x. I don't have a value for x, but I will find one. Dx dt is 4 and my y is 12. Now at the moment that the height of the ladder to the ground is 12, I can find how far the ladder was away from the base of the wall. So if I were to go ahead and use Pythagorean theorem to solve this here, oh, and I can't move it over. Let's move this over. This is 20. Oh, looks like my pen is